In this chapter, we are going to see how to analyze a given set of data. At intermediate level, you will not have practical sessions, but in exam, you will be given a table of results from some experiment, which you are then expected to analyze according to the questions set. The best way to understand this topic is through a number of different examples. Let us start with a very simple situation. Suppose we have an unknown resistor R connected in a circuit, and we are changing the current I through it by a variable resistor, each time noting both the current through it with an ammeter as well as the voltage across it with a voltmeter. In other words, we'll end up with a table of current voltage values. The aim of this experiment is to measure the unknown resistance R. V1 and V2, shown in the table, are called repeated readings, since, as you know, it is always a good practice to repeat a measurement at least twice. V bar denotes their average. In this experiment, the current and the voltage are those quantities that are changing and are hence called variables. On the other hand, resistance R is a constant. Moreover, we call V the dependent variable, whereas I is the independent variable, and this is because the voltage reading depends on the current setting and not vice versa. We normally plot the dependent variable on the y-axis, in this case V, and the independent variable on the x-axis, in this case I. But this is not necessarily always so. Now, from theory, we know that V is equal to IR. The arrows are used to remind us that V and R are the two variables in this equation. In fact, in any given equation, you will always have two variables. The remaining quantities will then be constants. In this case, we have R constant. When plotting a graph, our aim will always be to end up with a straight line graph. And this is because we can easily deduce information from a straight line graph. To ensure that the graph we're going to plot will be linear, we must arrange the given equation in the form of the general equation of a straight line graph, which is y equals mx plus c, where y denotes the y variable, m is the gradient, x the x variable, whereas c is the y-intercept. Now, to arrange the given equation, it's best to start by putting as subject that variable that's going to be plotted on the y-axis. In this case, it is v, and it is already subject of the formula. The other variable, in this case the current, will then obviously be the x variable, so we should go here. Resistance R must then be inserted here. Such that instead of V equals IR, we now have V is equal to Ri. Obviously here we have plus 0. Now you might be asking, why are we playing around with the equation in this manner? Well, the advantage of doing this is that by comparing to the general equation, we can conclude that a graph of voltage on the y-axis against current on the x-axis will first of all be linear with a gradient equivalent to the resistance, capital R, and the y-intercept, which is 0, showing that the graph should pass through the origin. The unknown resistance can be determined simply by calculating the gradient of the graph. So the gradient, which is change in y over change in x, in this case it will have a physical meaning, which is the unknown resistance R. And in general, the gradient will thus have units, which in this case are ohms. Let us now take another example, considering a car accelerating uniformly, meaning with constant acceleration. The aim here is to measure its acceleration and initial velocity. From theory, we know that v is equal to u plus at. The variables here are velocity and time. In other words, the velocity changes with time since the car is accelerating. Now, the crucial step is always to look carefully at the equation and arranging it in the form y equals mx plus c. If we leave the velocity v as subject, then it becomes the y variable. Time t is then the x variable, so it's written here. The acceleration must remain multiplied by t. And lastly, we have to add plus u. The equation is hence telling us that a graph of v on the y-axis against time on the x-axis would be, first of all, linear and with a gradient equivalent to the car acceleration. Moreover, the y-intercept would give us the initial speed of the car. Note that the units of the gradient, since the gradient is representing acceleration, so the units must be meter per second squared. I am here showing two sketches of the graphs one may obtain for such a situation, one showing an accelerating car and the other for a decelerating car. Notice that the line has a negative gradient, negative acceleration for deceleration. In both graphs, note that the y-intercept is equivalent to the initial velocity u. Now, in the third example, we have an object that is falling from some height s under the action of gravity. Hence, it accelerates downwards by g. G is the acceleration due to gravity. And the aim here is to determine g. We suppose that in this experiment, we varied the height. And for each height setting, we measure accurately the time of freefall. So the variables here are the height s and the time t. G is obviously constant. We find, however, that if we had to plot a graph of S against t, we would end up with a non-linear graph. And the reason is that in the equation, time is squared to the power of 2. If we look carefully at the equation and try to arrange it in the form y equals mx plus c, don't forget that our aim is always to obtain a straight line graph, then it is clear that the graph needed here is not of S against t, but of S against t squared. So on the x-axis, we need to plot t squared. And that would give us a straight line graph with a gradient equal to half g. So then g is simply found by multiplying the gradient by 2. In another example, we are going to measure again g, the acceleration due to gravity, but this time using a simple pendulum, as shown here. The experiment would involve changing the pendulum length, L. And for each length, we measure the periodic time, here denoted as capital T. Don't forget that periodic time means the time taken for one oscillation. So the variables here are capital T and L. Now, from theory, we're given the equation of a simple pendulum. Looking at the equation clearly shows that it does not appear to be in the form y equals mx plus c. And it is obvious because of the square root. In fact, if we had to plot a graph of t against L, the graph would obviously be a curve. So the first step must be to get rid of the square root. And this can be done by squaring both sides of the equation. So we end up with t squared is equal to 4 pi squared. Okay, so we square 2 pi, that gives us 4 pi squared, and L on g, obviously without the square root, which can also be written as 4 pi squared on g times L. The equation is thus showing us that rather than plotting the periodic time against the length, we need to plot t squared on the y-axis against the length on the x-axis. If we look at how we are arranging the equation here, so a graph of t squared on the y-axis against length on the x-axis should be linear, passing through the origin. How do I know this? Because here plus c, I'm not showing it, but it is understood that it is plus 0, and the gradient, which is equivalent to 4 pi squared on g. All right, don't forget that the gradient is always found using change in y over change in x. But then we are saying that we can also equate it to 4 pi squared on g. The aim is to find g, and this can simply be found by working 4 pi squared divided by the gradient. Let us now move on with drawing a good graph. The first thing to consider is the scale. I will here try to list a few guidelines to help you choose a good scale. The scale must be chosen such that the data points span more than half the width and half the height of the page. It is the data points that must be spaced out. Thus, extending the line of the graph does not help a poor scale. So here I'm showing the data points which are too close to each other, spanning a very small area of the page, and extending the line does not do any good. So this is due to a wrong choice of the scales. So having something like this is totally unacceptable, and you should start again by readjusting the scales. Remember also that the graph sheet of paper may either be used in portrait or landscape format. So you should try to evaluate both possibilities before deciding which scale is best for your data. The scales need not start from 0. You may choose to start at whichever value you want, which may be different for both axes, as I'm showing here. And you do not need to use any particular symbols, such as the one shown here, so there's no need for this. Just label the axes clearly with their values. So here, I'm clearly showing a value of 1 Newton for the y-axis and 0.1 meter for the x-axis. There's no problem with that. We start immediately with those values and move on. A good thing to check is whether the value of one box results in a recurring value. So for instance, if in this example I skip 3 boxes, so 1, 2, 3, and write down 0.2, then it is clear that the value of one box would be a recurring value, since 0.1 is not divisible by 3. Such a scale is said to be awkward and should be avoided immediately. Now, when it comes to plotting the points, this should be done carefully using a sharpened pencil to draw a vertical cross. Not an X, nor a dot. Please remember to label both axes, including the units, as shown here. And also add a title to your graph, which should be written in full as shown, for instance, a graph of force in newtons against extension in meters. The y variable, meaning the quantity plotted on the y-axis, should always be written first. So when we say a graph of force against extension, it is understood that this is on the y-axis, whereas extension is on the x-axis. It sometimes happens that the points you plot will not fall perfectly along a straight line. We say there is a small scatter, as shown here. What you must do in this case is to use some judgment to work out the line of best fit for your points. The straight line that passes evenly through your points is the one having approximately the same number of points above it as beneath it. So it is not that line passing through most points, as you might be inclined to think. So here I'm showing the green line, which is the correct one. It is just passing from this point, but the points beneath it are balanced by the points above it. So that makes it a correct line of best fit. On the other hand, the red line, even though it passes through 3 points, however, that is not a good choice, since it leaves 2 points above the line, which are unbalanced with no point beneath it. Let us now consider the gradient of the graph, which is sometimes also referred to as the slope of the graph. For the gradient, you must choose 2 points that lie on the line. So these must not be chosen from the table of results, since you might mistakenly pick out points that do not lie on your line of best fit. These 2 points must be chosen where the line intersects the grid of the graph sheet, such that they are close to the ends of the line. These can be encircled to distinguish them from the rest, and if another point is added, for the sake of calculating the gradient, then you can use an encircled dot to show that this point does not form part of your table of results. A good custom is to write the coordinates next to these points to facilitate the calculation of the gradient, which is calculated as change in y over change in x. So y2 minus y1 on x2 minus x1. Now, a few points about the y-intercept. First of all, what do we understand by the term y-intercept? It means that value on the y-axis for which x is 0. So it might not necessarily be that point where the line intersects the y-axis, as shown here. For instance, here we are showing a line that intersects the y-axis not where x is 0, but where x is 0.1. So this is not the y-intercept. In fact, the y-intercept is not shown by the graph. So what do we do in such a case? Do we need to redraw the graph and choose a scale starting from 0? And that would be the worst mistake you could do, since first of all, it is time consuming to start the graph all over again, and secondly, it leads to bad use of the space on your graph sheet. You could also face this situation, where even though the x-axis starts from 0, however, the line intersects in the negative y-axis, which is not shown on your graph. So, in such cases, what we do is simply that we determine the y-intercept by calculation. We start from the general equation of a straight line graph, which is y equals mx plus c. Hence we get y-intercept c is equal to y minus mx. Then we substitute for the gradient with the calculated value, change in y over change in x. And for x and y, with the coordinates of a point on the line, which could be one of the points just chosen for the gradient. So when drawing a graph, you must try hard to abide by these suggestions to ensure you end up with a correct graph.